We are going to return to cryptography now and discuss symmetric ciphers. We've actually seen some of these already, and so this is the idea that between two people who want to send messages to each other, we call them Alice and Bob, as we so often do in cryptology. And what we know is that Alice and Bob share a secret key that they use to encrypt and decrypt messages. So they determine what message they want to send, use this key to encrypt it, and then send the message to the other one where the other person has a similar key or the same key in most instances, and then uses that key to decrypt the message. So available to both Bob and Alice are a set of keys, okay, and so we're going to use a capital K to denote the set of keys, and then within this set, the particular K that they choose, we use a lowercase k for that, and then they each send a message M, lowercase, but those come from a set of all messages that they could send, and I use a capital M for that. And then also, so this is just the plain text that they send. So I'll just so they could choose any phrase from all possible phrases, and then they also get a ciphertext C from all possible ciphertexts, which I'm going to use as a capital C, and I'll write that just a little bit differently. Okay, so we have set of all keys for K, M for plain text or cipher or messages, and then ciphertext for what is encrypted. Next, once they have these, they have to establish encryption and decryption methods, and these really are just functions. So what we think of encryption as is that it is a function that, well, we have to know the message, right? So we have to take the message and the key. Okay, so it's a mapping from the domain that is a Cartesian product of M and K, and then it produces a ciphertext C, versus decryption is where we take the ciphertext and the key and produce the plain text M. And so really what we're saying is that if we look at the composition of these, it shouldn't be any surprise to us that if we take the key K and the encrypted message, which again we're taking as K and M. So if we take the decryption method, or if we want to decrypt using the the key K and the encrypted message, which this would in essence be our ciphertext C, then what we should get out is our message back. Okay, so inverse functions, right? All right, and so then one other thing is that sometimes when we're looking at this function E, so it is something that takes two elements and produces the decrypted message, or sorry, the encrypted message. Sometimes we just note this as E sub K of M, because really once we choose the K, we're really just interested in the message. So the key is just usually denoted as a subscript. This has to be one-to-one, and I want you to think about why. And so just as a reminder, one-to-one means that if we have, and this is generally if we have equal outputs, that forces us to say that the inputs are the same. Okay, so why must this be one-to-one? The textbook does say, it does go through the mathematical justification, but why more generally do we need this? Okay, now, so those are just some like backbones of what we're going to be doing here with symmetric ciphers. But now our scenario gets a little bit more complicated, because whenever messages are sent back and forth between Bob and Alice, or generally two people, there's a possibility that it could be intercepted by an eavesdropper. And so how, or is the message that we're sending secure? Okay, and the idea here is that, well, it should be secure, but really the idea of secure comes from what we call Kirchhoff's principle. And this says that the security, and I'm going to write this out, so security of the crypto system should only depend on the secrecy of the key. Okay, so note that when we were talking about the tools available to us, the key space, the message space, or the plain text space, and the ciphertext space, really all he's saying is that we should only really care about the key. Everything else, it could be intercepted, whatever, but the plain text should not be intercepted, but that ciphertext, that encrypted text, could be intercepted and still be secure. So that is to say, we could make everything public except the key, and we should still have a safe system. Okay, and so here, if a crypto system is successful, so again, we have the key space, the plain text space, ciphertext, encryption and decryption functions. Okay, the idea is that you have to have 4 properties, and so I'm gonna pause the video and write these out, and then resume once these are all posted. So make sure to take some time after and write all these down. And here are the characteristics of a successful crypto system. So 1 and 2, pretty straightforward. Easy to compute the encrypted message and the decrypted message given. For both of these, either given a message or a ciphertext. Okay, great. Number 3 is absolutely pivotal as well. So if we are given any of the ciphertext, so in event that it's intercepted, it must be difficult to decipher without knowing the key. Okay, pretty straightforward. The 4th one is desirable, but it's often hard to achieve. So if we're given a set of plain text and ciphertext, okay, and they're matched up, so we know that this this ciphertext corresponds to this message and vice versa. Okay, and we have a set of that. If we're given that set, we find another message not in this set, then it's still hard to decrypt it without knowing what our key K is, and this is called a chosen plain text attack. So this was what Enigma, if you've heard of it in the Enigma machine, it was the case that we ended up getting ciphertext. We didn't have the corresponding plain text, but over time we were able to figure out, okay, this bit of text, or this bit of ciphertext, corresponds to this message, and then over time we were able to break it. So these are the properties that we are going to look at as we go through the other videos for this section. So every cipher, or every scheme that we come across, we want to make sure that it is a successful crypto system. And if it isn't, well, then we need to make it better. Alright, so in the next video we will talk about a new type of cipher called the affine cipher, and then we'll get into some encoding schemes, and finally talk about asymmetric ciphers.